Welcome to this bite-sized session from our recent seminar, How Close to the Cliff Are You When Your Eyes Are Closed? With Philip Adams, CEO of Fabrics, we'll discuss the importance of the pathological test signal.
So pathological test signals for STI. This is a subject quite a lot of people will understand from the SD and HD days, but it's got rather complicated when it moves on to 6G and 12G testing. There's a really good paper. Can't recommend this enough. If you want to understand the subject, find this paper. It's Sumpty created it. Well, it's a Sumpty paper. David Brown and John Hudson are the authors of it. John Hudson's a pretty famous character within broadcast and has been heavily involved in a lot of the STI interfacing. He worked for Genum, which became Semtech, and he's one of the authors of this document. So I would strongly recommend reading this if you wish to go into pathological testing in detail. I've just got a few points to make here, I guess, on top of that. Please note that normal pathological testing is only ratified by Sumpty for SD, HD, and 3G level A. It's not ratified for 3G level B, 6G, and 12G. John Hudson was working on that, and I was working with him on bringing our products up to speed with the recommendations that were being put to Sumpty. But John was made redundant from Semtech, and it was never published. Sumpty never published the pathological test signal situation. So there's quite a story starts to evolve from here. The pathological signals are all because of something called scrambling. This is the scrambler, and this is the video data. These are the single bits of the video data, and I won't go into the detail of it. It would take us too long to do that. But this scrambler basically modifies the data. There's a scrambler here, and then there's a non-return to zero section here. The whole point is to ensure that there are sufficient transitions in the data stream to recover a clock signal from received data, especially that data contains some static data in much the way that video images can. This ensures that it's randomized and that it's scrambled. And it also provides long-term DC balance for the ones and ensures that you've got an even number of ones and noughts in the data stream. So this is all about getting the DC part correctly, etc. So documents available from Sumpty, I recommend reading it. This is some data that I've kind of taken from it, which I think are the main points taken from that document. We have two pathological types which break that algorithm. So the algorithm, I've got it here, the G1X, X9, X4 plus 1, plus the NRZI bit. It's got failure modes. It's got quite a lot of failure modes. And the two worst failure modes that have been identified are related to PLL testing and related to cable equalization testing. So these are what we now call the low frequency pathologicals. Now, this set of sequences on the interface can cause the scrambler to create this signal repeatedly, all the way from the beginning of the line right to the end. Won't do it always. It has a statistical chance of doing it once in every 512 lines. But when it happens, you get this sequence on the interface, which is really stressful for the interface. You can imagine trying to run a cable equalizer with so little data. You've only got these small pulses. You can get the opposite of this with single pulses going downwards as well. So that's one type of pathological, pretty stressful for the interface. Another type of pathological is the PLL test, and this is one where you end up with a square wave. So you've now got an interface which, although it's running at let's say 3 gigabit per second, 20 bits are high, followed by 20 bits low, and it continuously does that. So that's pretty hard for getting your PLL to work. You really are stressing your PLL. There are further tests, further failure modes identified in the document, something called potholing. As I say, I think we won't have time to go through that now, but potholing is something you need to worry about as well. So all these tests can be checked for by just creating a test pattern with these particular codes in them, and that's what we do. So that's done for SD, HD, 3G. When it came to working with 3G level B, 6G, and 12G, it all got a lot more complicated. It got more complicated because it was a more difficult subject. To create these signals, if you dig into the standards, you take separate streams with all their own TRS words, etc. You multiplex them all together. This creates much bigger potholes, but it also means that you're very unlikely to get the same pathological conditions on the interface. And the chip manufacturers tried to fight that for quite a long time, until they managed to get the chips to work. So there are some chips from many years back which may struggle with pathological signals, and you'll still get some that struggle today, especially optical interfaces, but some will work very well. So we've created some unique features, and I should probably just say what they are. This is the proposal that was being put through SMPTE of a new type of pathological. It had the PLL check, the EQ check, they're low frequency pathologicals. It had color bars, which is called a mid-frequency pathological, and it had high-frequency pathologicals, the clock pathologicals. And you can combine it all into a single test pattern. It's available on our products. And because the manufacturers were not happy to create receivers that worked with full pathological signals, i.e. occurring the full length of the line, we created the concept that you could insert as much of it as you wished. So you can see we've cut it off here. And this is probably looking at something like a 60 or 70% pathological rather than the 100% line. So you have that flexibility. You can work with that. You're perfectly limited to work with, say, a 25% pathological, and that would be okay. You know, as long as you made people aware that's what you're doing, that's probably going to be okay for most people in terms of receiving signals. But that's a kind of unique feature that we put together.
Yeah, so Phil, you've got a whole series of stress tools that you have created that are very unique to fabrics. And what are you stressing? Are you stressing the transmitter? Are you stressing the cable, the receiver? How do those stress tools exploring the limits of what we can do?
We created an advanced stress tool set to go with the as an option for QX range. A lot of it was to do with testing with MACOM and Semtech and TI. We worked with all those companies. We asked them what did they want, and they advised us as to what they would like, and we put a whole lot of tests together. These are quite advanced, so they're for more advanced testing. So normally you'll be looking at your eye pattern, you'll be looking at your jitter, and you'll just be checking that you meet spec, etc. as per the rest of this document. But we have some much more advanced tools. You can see here we're inserting jitter sinusoidal at a particular frequency, and you can see that you can see that here now. So in order to, one of the big subjects was eye amplitude measurement. For most people, the measurement tools we have in the standard products are fine. But if you're starting to work with oscilloscopes and other pieces of equipment which are not SDI based at the core, but you want to test the interfaces, then you'll come across something called Shorth mean. So we have the ability in the advanced tool to use Shorth mean as a method of measuring eye amplitude. This is a windowed method that uses pixels within a particular rectangular window. You position it on the eye waveform according to where the best indication of eye amplitude will be. And it creates this, it has the original histogram, but it has this new blue histogram, which is the Shorth mean histogram. And you can use that as an alternative method for measurements. And as I say, this is when comparing to alternative, more industry standard pieces of equipment. So that's just something to be aware of. It's pretty advanced. We put a whole lot of tools in there for testing interfaces from the generator side. So normally you'd be generating HD, 3G, 6G, 12G. You'd want signals to be single link, dual link, or quad link. And you choose your test pattern and whether you've got pathological, etc. So you choose that, but then you've got a whole lot of things that you can modify. You can play with something called sync bit insertion. You can turn that on and off. You can play with the scrambler and turn that on and off. These are useful if you're an engineer working in a lab and you care about checking the timing of signals leaving your product. So that's quite specialized. We created a PRBS generator. That was through working with MACOM and Semtech. They do all the chip testing using PRBS initially. It's far more scientific and far quicker to get repeatable results. So we created a PRBS generator which replaces the SDI data rather specialized, but allows you to use other pieces of kit. On top of that, optionally, you can do the jitter insertion all the way from 1 to 10 megs, all the way from 0.01 UI, right the way up to 128 UI. So an incredible tool there that allows you to create a signal which is really stressful for a channel, so you can begin to understand what the channel's doing. We can then modify the physical eye pattern itself. We can change the signal amplitude plus or minus 15%. SMPTE spec is plus or minus 10. So this gives you the ability to go beyond the spec and check that your receivers are working with the full range of spec. You can play with rise time, you can play with pre-emphasis, you can mute it, and you can do a signal invert. You can do all this using the REST API. So you can do it automatically, create your own test sequences, etc. Finally, you can insert bit errors into the stream. We have a pretty sophisticated bit error insertion tool which will insert. Now that's really useful for testing the performance of kit and to see how well it behaves when there are bit errors on the interface. Some kit behaves really well, other kit doesn't. So that allows you to understand what's in your critical signal paths and how well they're performing. So we have that tool set all applicable to the signal generator. And we have this path which allows you to monitor whether you've got pathological detection, pathological conditions on the interface. So this allows you to check that. This was all done with work with John Hudson and other interface experts. It was all to help them with their testing, but it helps manufacturers as well. Rather advanced, I won't go into any more detail on that. This is using that tool, but using the REST API. I'm just showing you inserting 0.3 UI of jitter, and we've swept it all the way from 10 Hertz all the way up to 6 mega, well, all the way, this is charting up to 10 megahertz. And you can see these are the different filters. You can see them coming in. So you can see how it's filtering the jitter and it's giving you readings. So this is proving to us that our products are performing correctly and to spec. And we do this to help ourselves. However, if you were to insert a third-party product between the generator and the analyzer, you could look at the transfer function of your own products. So it's quite an interesting tool set, and you can drive everything under REST API. With the PRBS tool set we created, we've also got a document, a white paper on that. You can download that. You can have a look at it in detail. And there's a whole lot of tools on the QX with the advanced tool set that allows you to generate these PRBS sequences, analyze the PRBS sequences, etc.
We hope you found this session interesting and informative. And if you'd like to learn more, there are further bite-sized sessions exploring the SMPTE specifications, eye pattern measurements, jitter measurement, and stress testing SDI signals with exploring the limits. If this has whetted your appetite and you'd like to learn more, then the entire recording of the interview with Phil is available to watch on catch-up on either of the YouTube channels for Leader Europe or Leader America.